All right. Let me begin. So I go by Bill Deal. I'm in Northrop Grumman. I've got my collaborators on the chart. We've got Caitlin Cook, Kevin Leong, Aaron Swanson, Gary May from Northrop, and we're collaborating with Jet Propulsion Laboratory. I'm listing Becca and Boom. I'm going to talk about three things. IRaST actually has two technical development areas, and at the very end, I'm going to introduce the SMICES IIP, which I'm also the PI on. For the next chart. So this gives kind of an overview of what I just talked about. So IRaST stands for Integrated Receiver and Switching Technology. It's actually two topics which are sandwiched together. Doing it that way because we share wafer fabrication, so it's reduced the cost and it gets two good ideas funded. And the first of those is a integrated receiver operating at 424 and 448 gigahertz. And I'll talk more about that in a minute. But we believe that would be a good receiver to operate in the upper atmosphere, and we're interested in using that for doing measurements on optically thin contrail cumulus clouds. The second is switching technology, and I've been getting funding from ESTO for a few years to work on direct detection receivers, which we found out on the TWICE project. We've got some, we got 1/f noise. We developed a technique on TWICE to mitigate the 1/f noise, but on this project we're developing more advanced techniques to do that. And we'll talk about our recent updates. And these techniques, which we're working on right now, would benefit other ESTO projects, including TWICE, SWIRP, and SMICES. That brings me to SMICES, which is a new IIP, which combines two instruments on a single instrument. The first of these is a 239 gigahertz radar, along with the accelerometers. And the way that instrument is going to work, it's ultimately intended for a space platform, which would be DC power constrained. So the way that instrument is going to work is the passive radiometers will be forward-looking, and there's going to be an intelligent controller on board to identify, on board to identify tropospheric features of interest, and it would then switch on the 239 gigahertz radar to do detailed profiling of the cloud. Next chart. Here's a quad chart for IRaST. As I said before, we're looking at reducing 1/f noise is the first of the tasks. And it can be brute force like Dickey switch, although Dickey switch at 670 gigahertz would have a lot of front end losses. So we'll show some more advanced techniques for that. And then you can see the other graphic. You can see there's an oxygen line and a water line at 424 and 448 gigahertz. And we've got LNAs, LNAs now at those frequencies, which would allow us to use a single receiver front end to receive both of those, split them out at the back end, and get sensitive measurements. I've got kind of our status update on the bottom. The radiometric validation for our Dickey switch radiometer was supposed to be in March. That was stopped by COVID, and hopefully it'll resume in September. Next chart. Shows a little bit more of the motivation for the integrated, for the switching work. And you can see here, these are measurements from the TWICE project. Steve Ryson was the PI for that. And we built this direct detection receiver, which you see in the center on the left. The entire receiver has about 200 milliwatts. Receiver has about 200 milliwatts of DC power consumption. To receive 670 gigahertz signal, it's got about a 20 gigahertz bandwidth channel. There's bandpass filters in there. Direct detection receiver and the video circuitry in there. And you can see on the top right, you can see 1/f noise measurements from the TWICE instrument. And you can see the blue line is without any 1/f noise correction. And the challenge is there's a lot of contributors to 1/f noise. There's 3 mimics. Each one of these are 8 stages, so there's 24 transistor stages. And then there's the detector diode itself. So there's 25 1/f noise contributors. And even though the sensitivity of this receiver is quite good, if you look at the 1/f noise, it's quite poor without correction. This was not fully anticipated, or not fully unanticipated, and we put in a provision where we would switch the bias on and off for the first stage. So you're still going to get the 1/f noise. You're not going to be able to correct for that. You're going to get this kind of indeterminate state where you don't quite know what the impedance is, but we can measure the output voltage at the output of the direct detection receiver in the off state, and use that with the calibration of the instrument itself. And numerically, we can correct for the 1/f noise. And you can see on the bottom right that shows measurements looking at hot and cold targets as a function of time, and you can see the corrected measurement on the bottom right. And by doing this technique, we managed to improve the NEDT from 4.75 Kelvin down to 0.88 Kelvin. That was kind of the starting point of this. We realized direct detection receivers at these frequencies are great because of their swap, but you have to worry about the 1/f noise a lot. Let's go to the next chart. And to do more advanced techniques, you have to develop switches. So this shows some results here. We developed using the same technology we use for our low noise amplifiers. We developed switching technology, also in the same MMIC technology, so you can, in principle, put them on the same circuit as the low noise amplifier to mitigate against insertion loss. And this shows on the top right, you can see this is done as a 2-port, but it's a single pole double throw switch with a common port and 2 output ports. But we terminated one of the output ports with a 15-ohm resistor. And in the center, you can see the measurements. This is a 220 gigahertz switch, and you can see we're getting about 3 dB insertion loss in the on state, and good isolation. That's still a lot of insertion loss. We'll talk more about how we're going to use these on the next chart. But on the bottom, you can see the measurement in the package, and you get a few more dB from the transition, but it's still a very usable switch. And going to the next chart. This is how we actually want to use it. So we have a 90-degree coupler at the input of the receiver, 2 LNA chains, another 90-degree hybrid. We're making use of the phasing of the 2 taps. And we can toggle single pole double throw switch to a direct detection receiver. And so half of the cycle, it's going to see the antenna noise temperature. The other half of the cycle, it'll see the reference temperature. And we're doing the couplers in a waveguide which can show a few tenths of a dB of insertion loss rather than the 3 dB insertion loss you saw through the switch on the prior chart. So by doing this, we should be able to mitigate against the 1/f noise of the entire chain. And the only impact we're going to get for sensitivity is going to be the coupler impact, and then we're going to lose about half the integration cycle. I'm running out of time, so I'm going to go faster. This shows integrated circuit, and it shows some measurement results of the on and off state. This is ready to do radiometric measurements. We can get into the lab. Next chart. Pseudocollider is the other thing we're looking at, and you can see on the bottom we have measurement results for 180 degrees phase shifter. It's got flat results across the entire WF3 band. Next chart. And just some more results on the phase shifter and package. Next chart. This brings us to the 424 volts 48 gigahertz receiver. And for that, we're interested in measurements in the upper atmosphere using the oxygen line at 424 and the water line at 448. Next chart. And here's some measurement results. We've got the measured LNA results. We show good gain, about 17 dB gain in package, and the rest of the receiver we have in assembly. We'll have that assembled by September. Next chart. And this brings me to SMICEs with 16 seconds left to go. We started this project about 4 months ago. There's a few key tasks. The first of those is we're building the radar using technology we have at NGAS for NGAS for the TWT. The radiometers are being built by JPL, and in the third year we're going to put the whole thing on an aircraft, and inside the IIP we'll do a